All right, so question 5. Now, I just reviewed this again, and it looks like it's going to take a little more time to flesh this out completely than I thought it would. But you see some previous scribble here, but I believe you've seen something like this before. But it says, using this right here, derive an expression for A, part A of the ideal gas, and then part B of van der Waals. Now, di or dP at constant T. This turns out to be something we've seen before, and I believe it's mu T. Where does that come from? You go back to your enthalpy section, chapter 2, and when enthalpy is a function of pressure and temperature, you see that in differential form that says the change in enthalpy will come from contributions from a change in P or a change in T. So you get two terms. The first one is the change in pressure term, and in front of it is the slope of a graph of H versus P. So one of the ways to restate this ugly-looking entity is to say, we watch how this enthalpy changes when we change pressure, when we hold temperature constant. We graph it. How does the enthalpy change because we change pressure? So that becomes the slope of an H versus P graph when you hold temperature constant. And that was given the symbol mu T, or the T may or may not be there, but you know what I'm talking about when you look at the notes. The other term is if there's a change in temperature. The slope of what enthalpy is doing or changing because we're changing temperature, and that is the CP. But in this question, it says derive an expression for this entity, which is this one, which is when temperature is constant. So how much does the enthalpy change of argon simply because we change pressure? And notice how the pressure change in this question is only from 10 atmospheres up to 11. So it's a very, very small pressure change, only 1 atmosphere. So when you get more practice at doing these types of questions out of the textbook or etc., you start to realize that sometimes when you have such a small change in something, they often make a few simple assumptions because you can almost see how this is going to play out. This isn't there because we're assuming that the temperature is constant. We're only looking at a pressure change. So this mu T thing, if it's constant enough over 10 to 11. So let me just forecast a little bit what we're doing with that. So if all you had was a pressure change, right? Because temperature was being held constant. So you could see how when you integrate this side, you'd get delta H, and then you would get mu T dP. And we know that in our question, we go from 10 up to 11 atmospheres. So it's very small. So it's almost like you're integrating from P1 to P2. If we make the assumption that this thing, and we're just told that this quantity is that, which is equal to V minus T. We already know that. So this is a way to derive this expression, which is also known as mu T. And then we're thinking one step further. This is ugly if you're doing a van der Waals because the volume cannot be isolated by itself. So we can't take the derivative of with respect to T. So what we're going to do is we know that this entity right here, the hint that was given to us right in the question is that it's going to be a 1 over, right? We can get T by itself for a van der Waals, right? So T will be, I think, 4 terms, right? You take that expression for T, you put it here, take the derivative with respect to V. So you'll get 1 over this stuff left over when you take the derivative of what T is equal to. That becomes this entity. So whatever this is can get inserted right here. So V minus T times whatever you had here will end up being this value of mu T right there. So now we go back to what we were thinking. If that was constant, we assumed it to be constant, you would get nothing but that. So you would get this times the change in P, which, by the way, we already know is 11 minus 10. So this delta P in this question is 1 atmosphere. And incidentally, the other thing that we notice here is, in order for us to get energy units of delta H, this is going to have to be liters. Liters multiplied by atmosphere. So it's almost like in units, you're going to get somehow liters for this, and this could be atmospheres. And we already know that 1 liter times an atmosphere is equal to 101.325 joules. That's the conversion. So when we do this derivative here, so in a nutshell, what I'm saying here is, for the van der Waals, you get T by itself. And I'm looking here, T by itself, you get 3 or 4 terms depending. Whatever, I got 4 separate terms, simply to, and why don't I go ahead and I'll show you that. So what I'll do is I'll flesh this out a bit here. So let's start this. If you were doing part A, which is a ideal, and you have this expression, V minus T, del V del T P. So you want the quantity, which is also known as pi T, I believe. So I want this for an ideal. So for an ideal, I know that V equals nRT over P. So now this says take the derivative with respect to T. So if I go dV dt, you can get rid of this ugly, it looks ugly to us, partial differential, if we just say if P is constant. So I write it in words, we can get rid of it, and we can just write normal derivatives is what it looks like, the full derivative, dV dt. Take the derivative, so that would be dnRT over P dt. You get nR over P d t, because you take out what's constant, right? Take the derivative like that, so that's 1, so you're going to get nR over P. Now, if somebody tells you the derivative with respect to V, the derivative of V with respect to T equals this for an ideal, and they put in sentence form, if P is constant, I can replace all this with partial derivative notation, which looks like this. Instead of writing a sentence, we put this, the partial differential in the brackets in this. So this weird notation replaces the need to state this all the time. So therefore, I can replace back over here in what we're supposed to derive, V minus T. This is that, nR over P. And interestingly enough, when the T gets multiplied back in, we quickly realize that this is also V. But we already knew this because mu T and di H di P at constant T for an ideal gas goes to 0, and we've just proved it. So everything we just did here, we're going to have to do for a van der Waals. And if you look at a van der Waals, what we've already talked about, we cannot get this by itself directly. So the van der Waals looks like nRT over V minus NB minus AN squared over V squared. You cannot rearrange this and get V by itself. You're going to get a quadratic. And we talked about this in chapter 2 and in our notes, it's in your textbook. To solve for V, straight out of your textbook, although there was a typo, here it is. There is a genetic formula you should already have. I put mine in molar, notation. Now it turns out in this question you have 1 mole of argon. So the formula I happen to be using right now, and I lied, it's a cubic, not a quadratic. If you're using molar volume, and this is all in your notes from before, technically the van der Waals looks like this. So in other words, if somebody gives you enough information for a van der Waals gas and you're asked to solve for the volume or the molar volume, this is the molar volume one, you get a cubic. So you substitute all your values in for P, B, T, and A. And in this case, you end up getting, you'll get 3 answers, like you will for a cubic. And only one of your answers will be real. The other 2 are imaginary numbers. They don't work. So this one will give you an answer in liters. Because we do have just 1 mole, this liters per mole answer will actually be the volume that your gas is occupying when we start out at 10 atmospheres of pressure. So you're going to need that volume anyway at some point in our calculation. But what we're going to do here is we're going to say this is actually equal to 1 over the derivative of T with respect to V. So one of the things you have to do, because you're going to need it when you're calculating this value, and you get the 1 over di-T di-V, somewhere in the mix here, you're going to need a volume. So we're going to need that. Secondly, we're going to have to isolate this in terms of T. And one of the forms that I find is this one, R. So when you algebraically solve for T by itself, this is what you get. So now you ask yourself, can I take the derivative of T with respect to V? So I think you can see when you take the derivative of T with respect to V, assuming pressure is constant, this first term, are there any T's in it? No, so that's 0. Wait a minute, it's respect to V. V, there is a V. So you're going to get P over NR. This term has no V's in it, so you're going to subtract 0. This one has a 1 over V. So this term might as well look like A and V to the negative 1 over R. So you bring down the negative 1 and subtract 1 from that, which will be, you'll go to the negative 2, right? So you'll end up with RV squared. This one, you've got AN squared BV to the negative 2 over R. So when that negative 2 comes down when you're taking the derivative, you're going to get a negative 2AN squared B. And if you subtract 1 from negative 2, you get negative 3, which will put this V cubed. So this quantity right here is this. So this term can be replaced with 1 over all this. So long story short, when you are working with the pi t thing, which looked like that, I'll call it mu t, you're going to get V minus T over del V del T P. V minus T. But we were replacing this with that. So now you get 1 over this, which is that. Whew. So to calculate this dH dP constant T, which is mu isothermal coefficient, or whatever they call it, the Joule-Thomson coefficient. It's going to equal this. But see, in order to calculate this, to go back to where we originally started this question, we need that thing. Once we have it, if we were to get just a number, we could put that number in front, which will be in liters, and multiply it by the change in pressure, which is just 1 atmosphere. If we make the assumption that it is constant enough over the pressure range to take it out like it's a constant. Because let's face it, if we're stuck with this and we want to integrate this mess with respect to P, that's a lot crazy looking integration. So technically, this could mathematically potentially be done, but because we're only doing the change of 1 atmosphere, we're going to make those assumptions. So you could calculate this, and let me just show you the mess. So you're going to see this entity in my notes, and I don't want to give away the exact answer, so I'm slowly bringing this up to here. Right. So look what I did in my own solutions. What you just seen us had, V minus, I put the T over all this mess. See how I called that A? I circled that. And I brought it right here. And I did this on purpose simply to prove to myself that this mess right here in the denominator is going to come up with certain units. Now look at the units. The units of all this, and you can see all the unit cancellation, is going to be liters over Kelvin. Liters over Kelvin. So I get a final answer of these 3 terms. So you're going to have T in kelvins divided by something, a number that's going to be liters per Kelvin. So obviously when this divides into the temperature, you'll have liters. So as expected, the final answer for this entity has to be in liters. So this denominator mass, I came up with 119.01 liters per Kelvin, as you would need it to be. Then you could take that number, put it right here, temperature divided by that number, subtract it off of V. You will get the quantity we were looking for, which we called mu, and it will be able to multiply by delta P. So that right here is essentially how you get your final answer. To get the change in enthalpy because pressure, you would have to make the assumption right here. You take it out front. We're going to assume it's constant over the 10 to 11 atmospheres of pressure change. So we can just do this. And your final answer is approximately, it's a negative number that is somewhere between 5 and 15 joules. So if you have a number outside that range, you know it's wrong. I don't want to give away the exact number, but that's it in a nutshell. So where are we at here? Yeah, I think we've just calculated it. There we go. So that's question 5.